Next example here, example 2, is a really interesting problem. And there's a little technique here that we're going to go ahead and use to solve this. So, example 2. Two runners start a race at the same time and finish in a tie. Prove that at some time during the race they have the same speed. Okay. So, if we think about applying the mean value theorem here, we have to somehow have a function. Now, the function, whatever the function is, in the mean value theorem, essentially the mean value theorem is a statement comparing the two different types of rates of change that we've been studying. We have the average rate of change and the instantaneous rate of change. So if we're trying to say that at some point their speeds were equal, so here's our equality from the mean value theorem. So if we want speeds to be equal, that means our rate of changes are going to be speeds or velocities, however you want to think about it. So our rate of change, each of them has to represent a velocity or a speed. And since we're trying to prove that there exists some time, that means the value c that we're trying to show exists via the mean value theorem, it means that that is going to represent time. So what does our function have to be in order for the rate of change of that function to be a velocity? Well, it needs to be a position function. So we're going to need a function that gives, so it's output, it gives a position at a given time. So in other words, we need a function that you input time and it spits out position or distance, however you want to think about it. And since we have two runners, we could think about possibly two versions of the mean value theorem, essentially. Because we have the one runner's position and we have the second runner's position. Now, we don't have to make this too precise, but essentially, this is what we need. So what I'm going to go ahead and do here is define two functions. Let f of t be the one runner's position at time t, and let's say g of t be the other runner's position at time t. So it doesn't matter which runner. One of them is going to be f of t, the other one's going to be g of t. So we now have two position functions, so each of which we can supply a t value, and then it will tell us how far that particular runner has ran since the start of the race. So let's go ahead and talk about that now. Let t equals 0 correspond with the start of the race, and let's say let t equal t final correspond with the end of the race. We're not told how long the race takes, so this could be any real number. In fact, it doesn't actually really matter because we're always free to rescale time if we so choose. So we could have just said this is 1 if we really wanted to. It doesn't really matter, but let's just say 0 we start, and let's say t final, whatever that is, t sub f, that's the finish of the race. So then, essentially, what we're going to do here is there's a nice little trick that we use oftentimes in math, and that is, and we've done it before with the intermediate value theorem when we showed that there were two diametrically opposed points on any circle on a map where the temperature is exactly the same at that moment in time. We actually subtracted. we let our function that we're going to actually work with be the difference in temperature. And here we're going to create a new function. So now let h of t be equal to the difference in their position. Does it matter which one you do? Could you have done g of t minus f of t? Absolutely. You could have definitely done the other one. That doesn't matter, really. What's important here is that we're taking a difference. It's not that you have to do this with a difference. You are able to go ahead and do this intermediate value theorem twice and then put the pieces together that way. It's a little bit different, a little bit more algebra. There's more things to worry about here, but this is a really clean way to do it. So let h be the difference in these two functions. So then, last thing we're going to say here is that, I'll say this and not write it, but f and g, they are position functions. So position varies differentiably, which means that f and g are both differentiable, and therefore they are continuous. And then whenever you take two differentiable or continuous functions and add or subtract them, the result is something that's also differentiable and or continuous. So the difference between two differentiable functions is differentiable. Therefore, h is not only differentiable, but continuous. So I'm just going to say that this is continuous and differentiable, which means that the hypotheses of the intermediate value theorem are satisfied. So check. So now what we know is that therefore, by the mean value theorem, there exists a time t equals c that is between 0 and tf, so it's after the start of the race and before the very ending moment of the race, where the not h bar, h prime of c is equal to the average rate of change. So h of t final minus h of 0 all over t final minus 0. Okay. So now, let's go ahead and expand this. Well, what do we know about h? Well, h is just f minus g, so this would mean the left-hand side is really f prime of c minus g prime of c. Same thing, we're going to expand this fraction. So the top is really f of tf minus g of tf minus, now we're going to expand the second term. This would be f of 0 minus g of 0 all over tf. So now we can go ahead and simplify some of these things. So for instance, what do we know about f of tf and g of tf? Well, we know that at the end of the race they finish in a tie, so that means their positions have to be equal. So they start, so both of these things. So they start at same location and end at same location, because they both began at the start, and if they ended in a tie, that means they must have started and began at exactly the same locations. So this tells us that f of 0 equals g of 0 and f of tf equals g of tf. So essentially these terms here cancel out to 0 and these terms here cancel out to 0, which means we really have 0 over tf and that's 0. So we know that the difference, f prime of c minus g prime of c, must be 0. Well, if the difference between two things is 0, that means those two things must themselves be equal. So what we've just shown is that if the two runners began at the same time, they finished the race at the same time, they ended in a tie, then there must have been some time during the race at which the two runners were running exactly at the same speed.